Hello, I am Chinmay Khanna from Section K and I have been assigned the processor Motorola 68000 architecture. And in this PPT, I'll be doing its case study and then its assembly code demonstration. The release year for this processor was 1979, a pioneering microchip from Motorola setting new standards. So basically, this was a new microchip that Motorola had released in 1979. Now it had the CISC architecture, complex instruction set computer architecture. So basically, it was offering rich and powerful instructions. And it also had a hybrid bus design which features a 32-bit internal architecture with a 16-bit external data bus, balancing performance and cost. And it had a general purpose use. It was widely adopted in early PCs, workstations, and iconic game consoles for its wide range. And it had a clean design. It was acclaimed for its elegant and straightforward architecture, making it easy to program and integrate. Now, moving on to the instruction set architecture, which is basically the ISA. It has a fixed 16-bit opcode size. So basically, instructions use a consistent 16-bit operational code with additional extension words for complex operations. And it has diverse addressing modes. So it supports a comprehensive set of addressing modes including immediate, register direct, register indirect, indexed, and absolute addressing. Move queue instruction. It enables fast loading of small constant values into registers, optimizing code and execution speed. BCD instructions. It includes dedicated binary coded decimal BCD instructions, simplifying decimal arithmetic operations crucial for financial and precise calculations. Now, moving on to the data path architecture of this processor. So it has data registers D0 to D7, which are basically 8 32-bit general purpose data registers for arithmetic and logic operations. And it has address registers A0 to A7, which are basically again 8 32-bit address registers, including the stack pointer for memory addressing. Microcoded control, which is basically instruction execution, is managed by a microcoded control unit, providing flexibility and efficiency. Then it has status register or SR. It stores condition codes and controls flags that reflect the state of the CPU and the result of operations. Then it has a 32-bit ALU, a powerful arithmetic logic unit capable of performing 32-bit operations, and a PC, which is basically a program counter, which is a 32-bit register that holds the address of the next instruction to be fetched. Now moving on to the pipelining structure, the Motorola 68000 basically operates with a non-pipelined sequential execution model, a characteristic of many early microprocessors. So now basically we'll be going through like the different steps there are for like this pipelining structure. So firstly we have fetch. It retrieves the instruction from the memory. Then we have decode. It interprets the fetched instruction. Then we have execute. It performs the operation specified by the instruction. Then we have memory. It accesses memory if required by the instruction, like for example if load or store is required. Then we have write back. It writes the result back to the register or memory. Now, the key characteristics of its execution model include no superscale execution. Only one instruction is processed at a time through the pipeline stages. So, at a time, only one instruction will be processed. Then, there is no out of order execution. So, basically, instructions are executed strictly in their order, and nobody here goes out of order in this processor. And then we have sequential processing. So, before moving on to the next stage, the previous stage is completed. Then here I have included this diagram in my PPT to showcase this pipelining structure so that it's more clear. Alright, then we have the simplified data path diagram. The data path illustrates the flow of data and instructions within the processor. So, firstly, there is instruction fetch, then there is internal register file, then there is ALU, then there is memory write back, and then there is program counter. So, firstly, moving on to instruction fetch, it retrieves instructions from memory based on the PC. Then internal register file. It stores data in address registers providing operands to the ALU and receiving results. Then ALU, which is the arithmetic logic unit, it executes arithmetic logical operations. Then we have the memory or write back. It handles data storage and retrieval from memory and writes results back to registers. Then we have the PC or program counter. It keeps track of the next instruction's address, feeding it into the address bus. And then finally, we have the control unit, which is basically like the orchestrator. So it orchestrates the entire process by issuing micro operations to synchronize all components together. Alright, so next we have a memory hierarchy. So, when the Motorola 68000 was released in the year 1979, its memory management skills were considered foundational. But now that we look at it as compared to modern architecture, they are quite simple to understand and they are not that complicated or that foundational. So, first we have the flat 16 MB address space, which provides a direct linear memory access model, simplifying memory management for programmers. Then we have the absence of on-chip cache. So initially when the 68000 was released, it did not incorporate L1 or L2 caches and it heavily relied on external memory access. Then obviously we have the external memory access in which all memory operations are performed via the external bus. So we require an efficient bus for this. Then we have the microcode assistance and the memory mapped IO. Now we'll be going through the specialized features and parallelism. So now the since the 68000 was released in 1979, it is not really built for modern day parallelism, but it does have some special features like the single core architecture, no SIMD or vector extensions, robust exception handling, flexible interrupt vectors, stack based operations, and reliable real time control. Then we move on to the historical significance and comparison. So here I have given a table in which I have compared this processor to the Intel 8086, and now I'll be telling you the importance of the 68000. So basically it's an iconic device and it is multimedia and graphics pioneer and it was programmer friendly. And so now in the comparison table you can see that the 8086 dominated the PC market because it was the IBM standard, but the 68000 carved out its niche in systems prioritizing user experience and graphical capabilities. Now we move on to the main part, which is basically the assembly program demonstration. So we were given two programs to execute, which is basically the factorial program. So I've taken out the factorial of 8, and then we have the Fibonacci program of the first 10 terms. So now I will be showing you the code for these two programs and explaining it. So firstly we have the factorial program, and the factorial program basically D0 is used as the countdown counter starting from 8 and D1 holds the result initialized to 1. MULU multiplies D1 by D0 in each loop iteration and the loop continues until D0 reaches 0. And the output for this code will be 40320, which is basically the factorial of 8. Next we have the Fibonacci problem explanation. So basically D0 and D1 store consecutive Fibonacci numbers. D2 stores how many Fibonacci numbers to generate. Add computes the next Fibonacci value. EXD swaps registers to shift the sequence. The loop runs until 10 numbers are generated. And the output for this code will be the first 10 Fibonacci numbers, which are basically 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. So this was my presentation on Motorola 68000. Thank you.